Hello students, in the previous lecture we had discussed power of an element and a semi-group or group in which cancellation law, semi-group is a group in which cancellation law holds true. And we also know that in a group then both the cancellation law hold true will be applied in further study. And in this we have derived that the laws of indices also hold in a group. Now in this lecture we'll just define first the order of an element and then prove something based on the order of element of a finite group. And we'll discuss finite and infinite groups. So let's define order of an element in a group. Let G be a group. Under the binary addition, one is under addition and second is under multiplication addition. So let us take A belongs to G. So we are discussing in this on the left hand side we are discussing algebraic structure. In G is a group, G is a non-empty set and with the binary coefficient multiplication, and the right hand side we are discussing G is a non-empty set with the binary coefficient addition. So the order of an element A belongs to G if there exists a finite least positive integer such that A raised to n is equal to E. N is the least positive integer. E, then order of A is n under the operation of the binary coefficient of multiplication. If n times A is equal to identity element 0, give the identity element for the addition of binary coefficient addition. So n times A is equal to 0 and n is the finite least positive integer, then order of A under the binary coefficient addition is said to be this is the order of A under the binary coefficient multiplication is n if A is n equal to B, where n is the finite least or smallest positive integers. So, and it is noted by order of A, order of an element of. If no such positive integer exists for which A is for n is equal to E under the binary computation of multiplication and n is equal to 0 for the binary addition, then A belongs to G is said to have infinite order. Or order does we say that order does not exist, or order we say order is G. If we can't find any positive integer for which A is for n is equal to E, or n times A is equal to E for addition, binary addition, this for multiplication, then A belongs to G is said to have infinite order. We'll say A has infinite order, or we'll say order doesn't exist, or we'll say order is G. In a group, if in a group we have identity element, so in a group the order of identity element is always equal to 1. So now let's discuss some examples. Discuss some example based on it. Let's consider the algebraic system G in one set with binary substitution is equal to ration number or ration number minus secret set 0 with a binary multiplication. So is equal. Now this contains infinite number of elements. So for the composition of multiplication, 1 is the identity element. So order of 1 is equal to order of identity element in a group is always 1. So when the identity element, the order of 1 is equal to identity element is 1. So now minus 1 into 1 comes out to be E, 1 identity element. So order of minus 1 is equal to 2 comes out to 1. So 2 is the least finite least positive integer for which A is power 2 is equal to 1. Therefore, order of minus 1 is equal to 2. In this algebraic system, this rational number minus singleton 0 with binary multiplication, the order of 1 and minus 1 exists, but the order of any other element except 1 and minus 1 does not exist. Note here. But In an infinite group, the order of an element may or may be this. Now, in this example, we discussed that in an infinite group, order of some elements exist, some may not exist. Same is the case in the case of in an infinite group. It's an infinite group in which order of we have deduced from this order of order of an element may or may not exist. So only two elements exist, but other element does not exist. Order of identity element of a group is always one. Now let's discuss another example. An example of a infinite set containing infinite elements. The order of each element exists. So let's consider a set of set Z set G consisting of Z such as the complex number and Z span is equal to 1 for some positive integer n. Some positive integer n. Some positive integer n. Now G, what is this? This is the n nth root of complex nth root of unity. So G is the union of all nth root of unity when n comes to n. So this is the union of nth unity are 1. You have derived it in the earlier examples, questions. G is 1. 1 is the identity element of this set. E is power 2 and pi by 2 pi I upon n, 4 pi I upon n, and so on to. So in this set, n is the order of each of this element. N is the order of each of the elements. Out of 1 is 1 because one identity element of this group, and but the order of other element is equal to n. So this is the algebraic system. This algebraic system is an infinite group with identity element s, and order of each element of is n, which is finite where n is a. Now it proves the thing based on the finite sets. Prove that in a finite group, the order of every element exists. In a finite group, so we have discussed the order of element in a finite group and infinite group. Now we'll derive theorem based on the order of an element in a finite group. So first image prove that in a finite group, order of every element exists. So given is let G be a finite group of order n. Let G be a finite group of order n means G has n elements. Let A belongs to G be an element. Out of these n elements, we have taken one element A. Now G is a group. G is a group. Therefore, this collection, after applying closure property to A into A into A into A, and so on and so on, we can multiply it a number of times. So this collection of powers of A are the elements of G, because G is group and closure property holding it. So these infinite number of elements, these are infinite elements, the elements of G. This implies, but the order of G is n. So means out of these infinite number of elements, only n elements are different. But the finite group, G is finite, and therefore the elements of first element first cannot be all different, because the infinite elements order of G is n, and the elements of G, therefore they are all cannot be different. Now let us suppose that any two elements of this set G, this set is set 1 are same. Let the A is equal. So I and G are positive integers, and we have taken two different elements, therefore I is not equal to J. And let us say that if any positive integer I is not J, so one of the two must be greater. Either I is greater than J or J greater than. So let us suppose I is greater than J for all I is greater than J for all I. And this say we have assumed that is I minus J is a positive integer. Now A belongs to G. G is a group, so A into J times also belongs to G, and A is for J belongs to G. G is a group, therefore A is for J minus J also belongs to G. So G is a group. In a group, cancellation law holds true. So After applying cancellation law to ai is equal to aj, write cancellation law to by a is to minus j, we got a is power I minus j is equal to a for j minus j is equal to 0 is equal to. So a is for positive integer, I minus j, what is I minus j was? If I is equal to j, so I minus j is positive integer. So a is for positive is equal to e. So well-ordered principle, if you write the numbers in particular order, the well-ordered principle, let m be the smallest positive integer. If you write these number in increasing order, decreasing order, this is the way we say, then is the m is equal to e. The order of an element, order of a exists and order of a is m, but a is an element of G. Thus, order of every element A is, but A is any element of G. But thus the order of every element of G, which is a finite set like this. Now we have taken any element. Now if you make A is an arbitrary element, so for each element we can take we take A belongs to G for another element, all n elements done by one. So we can find the order of each of them. If G is a finite group of n, then show that for any A belongs to G, there exists some positive integer R 1 is less than 2 R less than n such that A is finite group n. Next one is, if G finite group again of n, G has n elements, then show that for any element A belongs to G, there exists positive integer R such R, what is R? R is less than order of phase n. 1 less than R less than n such that is finite. A proof of this is similar to the first theorem. Given is, let G be finite group of n, out of G is n, and let A belongs to G be any element. Now G is a group, so multiply close bracket holds to in A into A into A into A square all belongs to G. What G is a group, close bracket holds to in. Now out of these and these infinite elements, let us consider n plus 1 elements. This one order of A is n, order of G is n, so means order of G is n, G has n elements, so let us consider one more than element G contains E, A, square, so n plus G. But order of G is n, so at least two of these elements are equal. Two are equal. Two possibilities, right? Either any of A square, n is equal to E or not equal to E. If not equal to means any two of the elements, these elements are equal. So now let us the first possibility. If any of them is equal to E, then E is for R equal to E. If any of them is equal to E, then E is for R equal to E. For all, one is less equal to, or one is less equal to R is equal to N, and R is the positive. So our result is 4. Now, if any of these elements not equal to E, implies any two of them are equal. So let us prove that AI is equal to AJ. AI is equal to AJ for some I and J, and one is less to I less than N, and one is less to J less than N, and I is not equal to J. If I is equal to J means we can, without loss of generality, we can let's assume that I is equal to J, say, therefore I and J is the positive basis. Now G is a group. G is a group. A belongs to G, so A for G also belongs to G, closure property. If A belongs to G, A for minus J belongs to G, because now using the G group, the cancellation holds true. Now applying the cancellation law to the this equality, A is equal to AJ by A is equal to minus J, right cancellation law, we got the A is for AI into A minus J, J into minus J is equal to AI minus J is equal to A, J minus J is equal to E. So let's put A I minus J equal to R, implies A bar equal to E for 1 is equal to R, and this percentage is now next thing is, let G be a group and A belongs to G be a G be of order M, is a group, and in G of order N order of element is given to us. Prove that E, A is to M minus or different elements, and for all n belongs to I, A is to N is one of the elements of this list. First part is given if G is a group, A belongs to G, order of A is M. This for A to M is equal to E. That is, M is the least positive integer for which A is M. Proof is the contradiction. Let, if possible, AI, two elements are equal. If possible, two of these elements are equal. Equal means AI is equal to AJ for if 0 less than equal to I less than M and 0 less than equal to J less than M, I is not equal to J, then without loss of generality we can assume that I is greater than J, say, or I is not equal to J. So as G is a group, so A for J belongs to G, A belongs to G, therefore A for J belongs to G, and A is minus J belongs to A. Or using right cancellation law again, so A for I minus J is equal to E, and is equal to 1 is less than I minus J less than M. Which is a contradiction? Which is a contradiction as M is the least positive integer for such that is bound to be. So our supposition that the two elements are equal is wrong. Therefore, hence all the elements of this are different. And next part is if G is a group and even if G order of A is M, our aim is to show that A for N is one of this. B A is M minus 1 for all N. Now for all N comes to I, N comes to I, that N is equal to N3 plus R. That means R is 0 less than R is right. M is the order of A is M. Order of A is M. M therefore now consider A is for N. Substitute the value of N. Here A is for M is equal to E, because order of A is M. So this is the B. So A is for N comes out to B is for R. 0 less than R is right. Hence, for all n equal to A for M is equal to A for R less than 1 implies A for M is someone of this. So, next thing is let G is a finite group and let A belongs to G be an element of order n, then A is for M is equal to B if and only if N is the divisor of M. So let G is a finite group and let A belongs to G be an element of order n, then if N to E, if and only if N to E. Now we'll prove the substitution part first. Given is G is a finite group, A belongs to G order of N. Given this is given, then substitute proof. If N is a divisor of M, that is N divides M, then this goes to Q such that by factorizing M is equal to NQ. Now take the left hand side of this, A is by M is equal to E, A is by M is equal to substitute M, is equal to A is by M comes out to E, G2. So if A is by M is equal to E and order of A is N, then we'll prove N divides M. Now in this case, we'll prove it by contradiction by using division algorithm here to show N divides M. So if let's divide N by M. We have to show N divides M. Let's divide N by M. So we get use the quotient as the remainder by division algorithm theorem. M is equal to N cubed plus R, where R is given as users and 0 less than R less than N. E can be written as A is for M. A is for M, substitute the value. A is for N cubed plus R, A is for N cubed. This is A is for N cubed, A is for R, A is for N is for QR, A is for N is equal to E is for Q, A is for R, A is for E is for Q is equal to E into A is for R is equal to, comes out to be equal to B. Implies where 0 less than equal to R is N, which is not possible because order of is N. So we from this we can do that A is for R is less than N, but order of is N implies N is the least positive integer for which this equals 0. Above result holds if R is 0. This will hold true if R comes out to be 0. So A is for 0 is equal to 1. Otherwise, A is for N is 0 is equal to E. That is M is equal to if R is 0, M is equal to N cube, or implies N divides N